My name is Sandeep. I'm a developer advocate at Google Cloud Platform. If you're here for the Kubernetes containers and databases talk, you're in the right place. With only a little hacking. So yeah, this is what everyone on the internet is yelling, like, can't do databases in containers. Containers are only good for stateless systems. Just don't even try. You'll run into a million problems because it's just not designed for it. Everyone knows this, right? Nah, I don't really believe in that. There's a lot of FUD around this, fear, uncertainty, and doubt. People tried it out. It didn't work for them 3 years ago, and then they just wrote it off, right? When Docker came out, yeah, it probably wasn't the right choice to run your database in a container. But the industry moves really quickly, and today, I think it is very possible to run a database in a container. What is a container? How many here can tell me what a container is? What is a Linux container? Anyone? No? It's just two things. Just a process of limitations. It's just a namespace and C groups. You take those two concepts, and that becomes a container. There's no formal thing called a Linux container. Solaris has like zones. There's jails in BSD. There's nothing called a Linux container. It's literally just namespaces and C groups. And so a namespace can basically control what a process can see, and a C group can control what a process can use. You combine that two, and you get some sort of sandboxing. That's all it is. It's just a process running that's isolated. Then what's the big deal, right? If it's just a process, what's the big deal? As if anyone who's used Docker before, you can tell there is a big deal, because this is what you need to do to manually deploy a replica set. Provision VMs, provision disks, install MongoDB on each VM, configure MongoDB, create a replica set, initiate the master, the replicas by logging into each one and typing in stuff, and hard code a bunch of IP addresses, and add another replica maybe, and pray your IPs don't change and your VMs don't go down, and I don't know what else is left. That's a lot of steps. Right? And you just give up and use something else. And of course, most of these steps are taken care of by something like Chef or Ansible, Salt, Puppet, Terraform, a deployment manager, right? No one is actually manually deploying a database by hand. I hope not. They're using something like a script to do it for them. But the problem is, sorry, not the problem. Docker lets you basically skip that installation step, right? So that kind of stuff. And Kubernetes lets you skip that configuration step. But this is exactly the same thing that Terraform or Salt or Puppet gives you already. So what is the big deal? The big deal is this part. That's like 99% of the time when you're running a database, you're maintaining it, you're keeping it up, right? You're not deploying it. Deploying it is a one-time thing. Maybe you do it a few times, but 99% of the time, you're keeping it operational. It's ops. So let computers do the stuff that keep you up at night, right? Don't take this operational complexity on yourself as a human being who has things to do, who has dinners to go to, who has sleep to do. Computers don't have to sleep. They run 24/7. So Kubernetes, what it really does for your database deployment is it simplifies that maintenance. And this is where things get interesting. I skipped over all that stuff because I don't think it's very interesting. I think this is where things really get interesting. So, and this is why people think Kubernetes does not work for databases. Because in the first thing that it came out with were these primitives called pods, deployments, and services. So for those of you who don't know what Kubernetes is, it's like kind of a 101. A pod is a group of one or more containers that share local hosts and are always scheduled together. So you can think of it as a container. It could be a group of containers, and we'll see that used in a second. Deployments, of course, just specify how many pods to run on your cluster. You say, I want 10 pods, and they run 10 pods on your cluster. And then the services are that stable endpoint to load balance traffic to this arbitrary number of pods. So it looks something like this, right? You have a deployment, you have a service. I deploy PHP and Nginx. I want 3 copies of it. Kubernetes creates 3 copies. The request comes in, and it gets load balanced to different processes running in our cluster. The problem is, if something goes down, it'll bring it back up. Great stuff. It's great for stateless applications. But this does not work for databases at all. We can't just have connections load balanced into our cluster. We can't just have stuff randomly spin up and spin down, crash and uncrash and just come back up. That's not how a database works. It's a very persistent, stateful store. So Kubernetes introduced a new concept, a set of concepts that will make it way easier to run databases inside a container. So the first thing is persistent volumes. So now persistent volumes are basically data volumes that persist even if the pod restarts or moves. What does that mean? In most cloud platforms, the disks and the compute are separate things, right? On AWS, you have EBS volumes. On Google Cloud, you have persistent disks. In Azure, you have, I forget what it's called, block storage. In all of these platforms, you can provision your compute and your disk separately. You can attach your disks to different compute VMs, things like that. They're not tied to the same machine. Kubernetes extends this concept because when you write data to a persistent volume, it's stored outside of that process. We also have a sidecar container. This is this sentence. It's a container that helps your primary container do some work. Take a look at how that works in a second. And then we have basically the thing that makes it all work, stateful sets. So stateful sets are a set of pods that can scale horizontally, just like a deployment, but they maintain consistent network and disk identities. So when a pod crashes and it comes back up, it'll still have the same network identity and it'll still mount the same disk, which is very important for databases. And finally, headless service. It's a service that does not do load balancing. So that's key, because you can't do load balancing for a database. But it exposes those pods directly with DNS. So let's take a look at how that works. So here's our MongoDB stateful set. The first thing it'll do is it'll provision a disk if it's not there already. Then it'll spin up one container. It won't spin up all of them at once. It'll spin up one at a time. And it'll boot up MongoDB. Then it'll do the second one and the third one. These configuration sidecars are a little bit of hacking that we have to do. They will actually talk to the Kubernetes headless service to discover the other members of the replica set automatically. So there's no manually logging in. There's no any sort of manual steps. They automatically configure each other. So this first one, it'll basically say, hey, I'm the only one here. I'm going to be the primary for the replica set. When the second one comes online, it'll automatically discover that there's already a primary in this replica set and say, I'll be a secondary. And the same with the third one. It'll say, I'll be a secondary as well. And so now when the requests come in, they actually bypass the service completely and hit each pod directly. So each one of these gets a static DNS name, Mongo1, Mongo2, Mongo3, for example. And so our app can connect to the full replica set without going through a load balancer. All right. So the other thing is Kubernetes really has sane defaults. It tries to spread your workloads over all the VMs, right? So it's not going to try to schedule everything onto the first VM. It's going to do some sort of round robins. I just got braces, so it's hard to talk. Round robin load balancing throughout your VM clusters. So you try to restrict it from doing some sort of silly failure domain type scenarios. But sometimes things need more formal rules, right? If you just use the normal stuff, it doesn't really know what it's running, so it's kind of do whatever best effort basis. But you might run into a situation that looks like this. You have a 3-node cluster. Each one of them runs a MongoDB instance. Great. They're all happy. One of them goes down. Things happen. Things break. Now Kubernetes will say, well, I still have some room on this machine. I'm going to reschedule you onto that one. With stateful sets, the disk gets remounted. Everything's working. But now each one of those is running at half performance. Well, that's not that good. And then this machine goes down too, because things always happen. If something can go wrong, it really goes wrong. But there's still room on that machine, so Kubernetes will reschedule that workload. But now you have 3 of these running on one VM. And you might think, oh, I have a 3-member replica set. I am highly available. If they're all running on the same VM, well, I'm not sure about that anymore. And the thing is, even if they come back online, because they're still technically running, Kubernetes will not reschedule the work onto those 2 machines. It'll just say, well, I have 3, they're running, they're fine, they're running on that machine. And then that machine goes down, and our whole database just gets downtime, right? And it'll take a time for it to basically restart on these and backtrack and do all that kind of stuff and boot back up. And all that time, we just have a bunch of downtime, even though we had 1 second ago 3 replica set members running perfectly fine. So Kubernetes introduces this really cool concept in the latest few versions called anti-affinity and affinity and things like that. So the first thing is resources. Resources, of course, you can say I need X amount of CPU, I need X amount of memory. That's great. You can also build custom schedulers, but that is outside the scope of this. But then affinity is something that's really cool and that was just introduced. So you have node affinity. So nodes are the VMs, right? So node affinity, you can say like, I want only one Mongo instance per host. So host name is like the actual physical node itself. So you can say, only one VM can only run one copy of Mongo, which makes sense. You can also say, I want only one per zone. So if you want to have a multi-zone cluster, you can say, I want one in each zone. Don't schedule 2 in the same zone, because if you have a zone failure, it doesn't matter how many VMs you have. Same thing with region. And then the rest aren't as important. The rest aren't as important for what we're talking about. Instance type is like a 1-core VM, a 10-core VM. For a database, you probably want to say how much memory and CPU you need, and then it'll do that automatically. OS, right? If you have a Ubuntu on one and Debian on the other, Arc, ARM, x86. Again, this is not super typical in most clusters. They're mostly just homogeneous. And then custom stuff. You can put your own tags on nodes and use it that way. Then you also have something called taints and tolerations. Again, this is not so particular for databases. Maybe if you're running something like mapd or a GPU database, you can actually say this VM has a GPU, and and it's tainted. So taint is a weird word. It's a very negative connotation, but it basically means like I have a GPU. So if you don't need a GPU, you don't schedule on me. Go schedule on another machine that doesn't have a GPU, right? So you can say never schedule anything that cannot tolerate a GPU, or prefer not to schedule something that can't tolerate a GPU, for example. So this also happens with dedicated hosts. This is more applicable to databases. Some people in certain on-prem SaaS situations say every customer needs their own particular machine. You can do things like that with this. And then finally, probably the most useful for something like this is pod affinity and anti-affinity. So you can just say, you never schedule our database on another node that already has the database. Simple like that. So you can say never schedule 2 on the same host. And so when we go see back to our example here, I'm just going to go back here. What it'll do is when it doesn't have this available, instead of scheduling it on there, it'll just be in a pending status until that VM comes back, and then we'll schedule it onto that VM, which is much more better than this horrible failure scenario. All right. So that is basically slides. Ooh, that was fun. That was basically slides. Those were boring. Demos are much more fun. I'm going to do something that looks like this. I'm going to launch a replica set on a Kubernetes cluster, scale it up, scale it down, scale it back up, because why not? And then I'm just going to log into a container and just stop MongoDB. I'm just going to just kill the process and see what happens. Then I'm just going to delete the container completely and see what happens. And then I'm just going to delete a VM and then also see what happens. For a lot of these things, if this happens, you either have to have some sort of watcher process doing something, or you get paged in the middle of the night. But we'll see how Kubernetes just kind of deals with it. All right. Oops, I'm gonna go back a percent. OK. So here's my cluster. I have a 6-node cluster on this running in our US West data center. Don't worry about this. That's all of Google running right there. So we have 6 nodes. If I go back to my disk section, you can see that each VM has a disk, but there's no special disks already created for MongoDB. Here is our deployment YAML file. So this is all we need, basically, to deploy our replica set. So the first thing is that service. And you can see that it's opening on MongoDB's port. No one can read that. I'm going to make it a little bigger. The cluster IP is none. That's because they don't want any load balancing. And we're going to select the Mongo pods. Then we're going to create a custom storage class. Now, this is not really necessary, but I like doing it. This is available on basically all cloud platforms, and even on-prem if you have something like a SAN controller or something like that that supports Kubernetes. So I'm going to say, I'm going to use our persistent disk SSDs, and I'm going to call this fast because SSDs are fast. And here comes the most important part, which is our MongoDB deployment or stateful set. So I'm going to say I want 3 replicas. I'm going to give them role Mongo. I'm going to say the termination grace period is 10 seconds. This is just a thing, so when it's a forceful eviction, it'll give it 10 seconds to kind of clean up all of its running processes and things. You can change that to whatever you want. Now I'm going to run the standard Mongo container from Docker Hub. And I'm going to run this command. So I'm just going to start up replica set 0 with some flags. And then I'm going to mount this volume. So this is our Mongo persistent storage. And it's going to be /data/db, which is where MongoDB writes its data. So that is actually this volume claim template. And what we're going to do is actually use that storage class to automatically provision a disk for us on the fly. So it's going to say, if that disk doesn't create a 100 gigabyte disk for me, and then attach it as data/db. And then finally, this is that sidecar that's doing that automatic configuration. You can see that we just passed it some environment variables that says what our MongoDB pods are. So role Mongo, environment test, and then this is the image for that. So that's just a Node.js process that's going to do all that configuration for us. All right, cool. So let's just deploy this. So what I'm going to do is, no one can see that either. So I'm going to say kubectl apply f for file, and then just that file that we just saw. So here, we can see it spinning up. This is my awesome dashboard. So you can see that those just switched from pending to bound. So it created those 3 disks on the fly. And now it's creating each container one at a time, right? So the first thing it's going to create is Mongo 0. It's in the container creating process right now. We also have our Mongo service with none for cluster IP because it's not doing any load balancing. I also have a, it said Mongo down a few seconds ago. Now it says Mongo up because our first instance has started. So I have something called Mongo test, which is a silly process that just pings MongoDB over and over again. And then just writes data, or writes a timestamp. So we know that MongoDB is currently up and running. So now we have our second member of the replica set up and running. And then this is just going to clear the database every 20 seconds because this curl becomes too long, so can't see anything. And then finally, we're going to have the third one. There we go. So now we have our 3 set replica set already created with just one command, basically, right? Just one create command. But you could have done that with Chef or Puppet or whatever. So it's not too impressive. What is impressive is you can just do something like kubectl scale replica stateful set. Mongo. So now it'll just scale it up to 6, and ta-da, we're going to get 6. So you can see that those 3 new disks got created on the fly, and it's going to create those 3 new replica set members. Now the other thing to notice here is the node names. So you can see that they're all running on different nodes by default. I'm not actually using any sort of affinity or anti-affinity rules here. I'm just letting Kubernetes take care of it by default. And it's smart enough to try, because it knows it has 6 VMs, it's smart enough to try to load balance that traffic over all 6 VMs. So it's going to wait for that last 2 to come up, and then I'll scale it back down. Oh. It's going to, there we go. All right, last one. So So here's the interesting thing. When I scale it back down to 3, it's going to terminate those old containers. And the interesting thing is, it's going to scale it down the same way it's scaled up. So it's not going to just destroy Mongo 1, Mongo 2, Mongo 3, like some random ones there. It's actually going to scale up and down the same way. So if you ever used Kubernetes before, you know when you just scale up and down, it just does random stuff. It just kind of just picks random pods to terminate. When you do it with, this is just, and so when you do it with a stateful set, it actually does it in a stateful way. There we go. Yeah, watch. I'm just doing a watch on a giant command, so sometimes it gets kind of stale. But anyway, back down to 3. But the interesting thing is, we still have 6 disks here, right? So the disks did not get deleted. They actually stay, you can delete them manually, but by default, if you scale back up to 6, it'll attach those old disks back to the other pods automatically. So if you have a bunch of data already stored, you don't have to replicate it all over again. OK, so now let's do some fun stuff. Let's actually go into one of these pods and just kill MongoD. Or first, let's actually look at this really quick. Bash. So if we exec into if I run MongoD, you can see that. What happened? MongoD. Oh, whoops! We're already inside. Let me exit that. Let me just run MongoD here. Anyway, let's just do this. Let's just kill it, because I don't like it anymore. So here you can see it's all 3 of them are running. So if I go kill -9. Who knows the kill command? I've forgotten it now. Let's see. Do I remember how to kill? Let's run that. Oh, there it is. So, well, that was too fast. Let me try a little differently. It will detect that. It'll say completed, so it actually crashed, right? And it'll restart that pod because it realizes it's not working. So you can see Mongo's still up because the other replicas. Let's see. Restart. There we go. So now it's automatically back up. So it says it restarted twice. So it detected that MongoD stopped running on that container, and it restarted that container itself. So you can see that it didn't actually shut down the whole thing and start it back up. It just restarted that one particular container. So it's running on the same host, the same IP address, things like that. So we'll just rejoin the replica set and be happy. Let's just kill that. Let's kill this one. Why not? Try to kill the primary. So let's see if we can kill the primary. So it automatically restarted. It restarted too fast. OK, so it's restarting pretty quickly. Let's try something a little bit more violent. Let's actually just kill the whole pod. All right, so now this is going to go away in our 2 seconds. So you can see that It just restarted. Too fast for us. Let's try this one more time. So it restarted, so you can see it's 30 seconds old. And it has a new IP address, but it has the exact same DNS name, which is what we're using in our app. So in our app, all we have to do is we're doing something like this. We're connecting to mongo0.mongo, mongo1.mongo, and mongo2.mongo. And so even though the IP address changed when the pod came up, it doesn't matter, it just connects to the same one. So now let's do something a little bit more violent. Let's actually delete a lot of them. We're going to delete all 3 containers. I'll stop that. You can see here, it's now creating them again from scratch. So obviously our database is down because it's not running at all, which is why this make is failing, because it's just hanging at our process level. That's OK. We'll just watch that. So you can see it's already back up and running. So if I run make, see if this make works. Yeah. Let's just do this. Let's just go ourselves to that Mongo test. Yeah, my front-end app is what's crashing, not the database. That's OK. Let's actually just delete this. So what I'm going to do is just delete the front-end app. Now it'll create a new one. So it'll create a new front-end. Obviously, you should have some better retry logic than my just infinite hanging, because that's terrible. Let's wait for that to come up. And so it's actually pulling down those containers onto a new host, which is why it's taking a little bit of time. But our Mongo, even though we killed all 3 of our MongoDB instances, they're already back up and running. And it took like something like 10 seconds. And of course, our MongoDB replica set has a 10-second-ish, what do you call it, re-election period. So when we have downtime, it's really just about 10 seconds of downtime. You can see it's already back up. And some of the previous data is still there. I know you can't, the timestamp doesn't really come through properly when it's printed like this, but this is the first time we visited this website. So all this data is already in those disks. And even though we killed all those containers, because it's remounting the exact same disk, and I think I can do make now. Yeah, there we go. It's remounting those exact same disks. So all the data that was there before is still there. OK. And so obviously, if we can also delete a VM. So I can say, let's just do it this way. I will go into my VM instances and just delete one. Let's see which one has a running MongoDB process. W6MX. Delete. So even though this instance is going to get deleted, we'll see what happens here. It's going to detect that it's not running anymore and then move it to another host. But because that disk is not attached to that VM, so you can see that here that it's attached to these VMs right now. Once it detects that VM is dead, it'll detach that disk from that VM and attach it to the correct VM that's running the pod. And you can see that the other 3, because we scaled up to 6, they're just sitting there unattached, right? So if we scale back up to 6, these disks will reattach to the correct nodes. So let's see what happens. Fortunately, shutting down an instance takes a little bit of time. OK, there we go. It is gone. So let's see what happens. So the health checks run every X seconds. You can specify this yourself in whatever you want. that up. Okay, so you can see that it detected that Mongo1, that VM was down. So now it's creating the container, but on a new VM automatically. And so the database is still up because it re-elected a new primary, and we're good to go. So even though I tried pretty hard to kill it, it was pretty hard to actually take the database down. The only time we did is when we killed all of them. Obviously, if you kill the primary, it does a re-election, and it'll take whatever X amount of time to kill that re-election, to do that re-election. But that's just like anything else. So even deleting a VM, deleting containers, deleting whatever, doesn't really matter. It's pretty resilient to all of these failure domains. But the nice thing is there was no manual steps involved. I didn't have to log into any of those containers and reconfigure them at any point because it all does it automatically. All right. So what is kind of next? Who's heard of an operator? Nobody. So this is something that CoreOS released a while ago. And it's actually really cool. They're built specifically for stateful applications like databases, caches, monitoring systems, etc. Right? So they released some operators for some of their products like etcd and Tectonic. I've seen a really cool one for Postgres. I'll show you that one. So this is called the Crunchy Data Postgres operator. And so what an operator is, it's trying to replace a human ops person, right? So it basically creates a custom Kubernetes object that has commands that make sense for a database. So like create database, destroy database, back up, restore, things like that. And you can see you just run this like pgo, show database, create database, delete, create, backup, and it's pretty straightforward. And basically it's just using the Kubernetes API under the cover, using these primitives like stateful sets and pods and services under the covers, and just abstracting that away for you. So this takes care. So in our case, we used that sidecar, that little sidecar container, to automatically configure MongoDB to like automatically join the replica set and things like that. With these new things called operators, you just kind of download this operator, and it creates a new like MongoDB object in your cluster that you can just create, which is really nice. It's very similar to what we did, except it takes it one step further, which is really nice. So I really hope someone builds a MongoDB, MySQL, just all the databases, people build operators for them. There are a few startups doing it right now, but it's still pending and in stealth mode, so who knows what that means. Let me turn these off. Awesome. So let me go back to the slides. So I think operators are going to be really cool. It's really easy to make them too, and I think this is like a really good quote. An operator represents human operational knowledge in software to reliably manage an application. Right? You're taking the DevOps knowledge that you already have in your. You have a playbook for X, right? Just make it into software and deploy it. So then your ops team can do more important stuff with their time, like supporting new applications, things like that, instead of just doing a lot of toil and just working on boring stuff. Yeah, thank you guys so much. It's the first time I've given this talk. I finished it this morning, so quite a few rough edges, but the code should be on GitHub soon, and you can follow me on Twitter at my full name. Thank you. And we have time for questions. If anyone has questions. I had a lot of these pieces before. From the first time I did MongoDB on Kubernetes was last Percona, when stateful sets weren't a thing. And so I really hacked together a solution like bash scripts and stuff to like make it work. Since getting stateful sets, I have a blog post about it on the Kubernetes website. It took me about a month to figure out like everything. And like I had to like basically write the sidecar container to like do the auto configuration and stuff. For someone who just wants to use this stuff, it'll take about maybe, I want to say realistically like a month to learn Kubernetes really. But once you know what Kubernetes is, maybe like 2 days to figure this out. Yeah. Good resource for Kubernetes. The Kubernetes website is great. CoreOS has a lot of good docs. If you follow me on Twitter, my blog is pretty good if you're interested in doing database stuff. Not a lot of people are doing a lot of database stuff. I think those crunchy Postgres GitHub that I showed you, that thing is pretty cool. It goes into a lot of detail. I mean, they do a really good job. They have, I think what I talked about today is only the tip of the iceberg. Backups and restoring and things like that are really important. So they really go through and really deep dive into it. Because that's kind of their business. Yeah.
Hold on. Have you go through some of the considerations when you were designing like the self-configuring sidecar and things you kind of had to work with?
Yeah, so it was an open source project, so it's a few people working on it. It's just like a side project that people are doing. Some interesting things. It's just a Node.js script that basically configures the MongoDB that's running next to it, right? So what it's doing is it's just blindly looking for all the IP addresses and then just hard coding them into the rs.conf. So it's not really smart right now. It's not doing any sort of like smart stuff. A few things bugs that we found were like when all of them were down, it would start adding itself as the primary, and then it would just have contention. So instead of that, it waits now at the stateful set that one comes up at a time. It's actually doing a little bit more smarter things like, if the replica set doesn't exist, then you do the primary. Otherwise, you actually join that replica set and start trying to make your own and doing a lot of weird things like that. Like, the code is all open source. Let me see if I can. There we go. Nope. Let me see if I can just find it here. It's called. So it's all open source here. And if you go into these examples, so if you look at the source code, that's not right. Let's see. So basically it uses these files. So k8.js is the Kubernetes API. Worker.js is actually what's going to do this stuff. And if you look at Mongo.js, you can see it connects to localhost because it's a sidecar, so it's actually because they're running on the same localhost. It tries to get the database, then it does a bunch of it's just a loop that runs forever, just checking, am I in a replica set? If I'm not, then let's join a replica set. If something happens, right? So it's just a bunch of just loops. And it's pretty straightforward, and that's why I think all this code should not be in a sidecar. It should really be in an operator. An operator is a lot better than a sidecar for other reasons as well. If the operator goes down, it doesn't affect the running Mongo processes. If this container dies and it maybe corrupts the Mongo process running next to it, that's a bad thing. It's pretty naive right now, but it just works. So that's why I like it. Yeah.
Yeah, I want to know what stages are you with applying this to RDBMS like MySQL, and with this, if you are using MySQL or any other RDBMS like Postgres.
Yeah, so this one is literally for Postgres.
Okay, now if you are not using anything default, you decide to use non-default port, non-default data directory. Can you squeeze that into this setup?
If you're using non-default data entry?
Let's say non-default port number for your.
Oh yeah, of course.
This can come in somewhere.
Yeah,
non-default data directory, non-default.
So I can specify whatever port I want right here, right? So it's that's MongoDB port, so I used it.
Okay.
When you run Mongo, you can give it a flag that says what port it should listen on. Okay. So for example, I can put whatever I want. Ports are not an issue at all. You can put whatever you want.
And MySQL, what level it is?
Anything you want. Anything from 0 to whatever the highest port that you can think of that's supported by Unix.
Okay.
The thing is, Kubernetes under the covers does a lot of port remapping and stuff. But for you as an application developer, or a database deployer, I guess, you don't have to worry about all that kind of stuff. It does a lot of IP tables, routing, and stuff to make the mesh networking work and things like that. But at the application level, you can use whatever port you want, and you're good to go. Yep.
Is this basically the same mechanism behind Cloud SQL? Is that the father of?
So this is similar to how we run stuff on Borg. So Borg is our internal container scheduler. That's kind of like the grandfather of Kubernetes. And so we run all of our databases. So like, for example, our persistent disks run on containers, right? So like, it's similar to that. I think that's like a lot more complicated because it's a lot older. Cloud SQL runs, does not run in Kubernetes. It just runs on VMs. I think the PM for Cloud SQL is here. He's giving a talk right now. So you should go try to talk to him. As far as I know, we schedule those workloads using something like this, but they're running on a VM per customer, right? We don't want to put two people's stuff on the same VM. So it's not like we have a giant cluster and we have a bunch of Cloud SQL instances. It's like one step above this, right? Yeah.
Got it. Thank you.
Yeah, Cloud SQL is just MySQL, right? So it's just doing the normal stuff. Cool. We're good? Good. Awesome. Thank you all so much.